Hello everyone, thank you for watching. The name of this work is Unstable Flow in Compositional WAG Injection. The objective of this work was to improve our understanding of the complex process involved in WAG injection in an unstable flow scenario, in our case using a gas with an adverse mobility ratio with oil. To that end, we combine A, the WAG hysteresis model of Larsen-Scott, B, the methodology developed by Sorby et al. To simulate viscous fingers, and C, fluid models with similar properties but varied degrees of miscibility. In our simulations, the water injection is stable, while gas has an adverse mobility ratio producing viscous fingers. To model the gas unstable flow, we use the methodology proposed by Sorby et al., which in a very summarized way consists in 1. Use of a gas-oil flow function that gives a high saturation and high mobility ratio for the gas shock front, and that also maximize the gas mobility along the fingers. And 2, user randomly correlates permeability fields so that viscous fingers can be seeded and a fine enough grid to resolve those fingers. To understand the impact of the miscibility of the gas oil system in our WAG injection simulations, we use fluid that have the same single phase gas and oil properties, meaning that pure gas and pure oil in place will have the same viscosity and density at the reservoir properties. But those fluids have at the same time different degrees of miscibility. To achieve that, we set most of the PVT parameters for all fluid models the same, while changing the binary coefficients between the CO2, which makes up the gas phase, and the other hydrocarbon pseudocomponents, which make the oil phase. For example, in the immiscible case, we increase and use very high values for the binary coefficient so as to increase CO2 repulsion between it and the other oil components, doing so raising the minimum miscibility pressure of the system or reducing its miscibility. At the same time, we had to use a very negative value for the C1 between the other oil components to avoid the C1 going to the gas phase when the phases are split, and so obtaining an immiscible fluid where the CO2 never mixes up or vaporizes the oil components. And our final step in our methodology is to define the WAG model. Our WAG injection is basically one slug of gas followed by one slug of water. Each slug has 0.1 per volumes, and this is repeated 5 times, totally 1 per volume of gas and water injected by the end. The WAG model parameters are set in this table. This is the dampening coefficient, or the alpha, the Lenz's constant, and the constant that links up the oil residual saturation in the Stone 1 model to the trapped gas saturation. Finally, these are the water-oil relative permeabilities, the two-phase and the three-phase water-oil relative permeability, and this is the oil relative permeability in a three-phase scenario using the Stone 1 model. And now we change for the results section. In this figure, we can see first the gas saturation for all 3 different fluid models, and also the CO2 normalized concentration, which is the CO2 concentration in both gas and oil times 1 minus the water saturation in this case. And this is plotted after the first slug of gas injection, so right after 0.1 per volume of gas being injected in the model. For the immiscible scenario, we can see a very similar profile, and that's what we expected, of course. The gas is mostly pure CO2. And we also see that the gas liquid relative permeabilities that we use do produce sharp fingers in our model. In the near miscible case, we see that these fingers are even sharper though, and that happens because of mass exchange effects dominating the shock front of the flow. As we can see in this figure in here, this is the shock front produced by the Buckley-Lever equations in a 1D model. But if we account for the mass exchange, we see that you have an even higher gas saturation at the shock front in the near miscible and of course the miscible scenario. And finally, we see that there's a big difference between the gas saturation plot and the CO2 saturation plot. Although we do see fingers forming the miscible case, we see almost no gas in it. And that's because most of the CO2 is condensed in the oil phase and not on the gas phase. So now we look at oil recovery for 4 different scenarios. First, the gas injection, then water injection in blue. In purple, we have a water alternate injection, but no hysteresis being considered in the simulation. And finally, we have a water alternate gas injection with the hysteresis model switched on. For the gas flood and water flood scenarios, we inject respectively 1 per volume of gas and 1 per volume of water. So we inject 1 per volume for all these models so we can compare them. As expected in the miscible case, we see the largest impact in both by switching on the hysteresis. In the near miscible case, we also see a very good increase in the recovery when using WAG, even without hysteresis being considered. We also see that in the miscible case where the gas injection is actually produces an actually higher recovery than the water injection. And that can be explained because the water flow in our models is stable, and so it gives us a very good aerial sweep efficiency, although its linear displacement of the oil is not as good as the gas in the near miscible case. It contacts parts of the system that was left behind by the gas in both these cases. And that happens because the flow of the gas is not stable. It produces fingers, and you also have gravity segregation happening. Also in the near miscible case, as we see in the immiscible case, WAG hysteresis effects also increase by almost 10 percentage points the recovery, so it has also a very good effect in the near miscible case. But on the miscible case, we see almost no increase when we switch on the hysteresis effects, and that is because there is almost no gas in the model, and the WAG hysteresis model that we are using is dependent on the gas phase actually appearing on the model. If we look at the recovery for the individual oil components in place, for the near miscible case especially, we can see that, for example, in a gas flood situation, we'll see a very big spread between the lighter oil components and the heavy oil components. That's because the CO2 in this case strips the oil of its lighter oil components and leaves behind the heavy oil components. But now if we look at the results for the WAG injection, we see that this spread is very much reduced. And that happens for 2 reasons. One is that the water displaces all the oil components equally. So just by injecting water, we reduce a bit this spread. But also because WAG hysteresis effects mean that when we trap gas in our model, we are reducing the oil residual saturation. And that means that now the heavy oil left behind, which has a small saturation and is immiscible by the gas, and so it's otherwise not very mobile. Now, when we reduce the residual saturation for the oil, this heavy oil left behind becomes mobile, and so it can be mobilized by both water and gas. An interesting result in our simulations is that a large part of the gas trapping is actually being done by the oil phase and not the water phase. And that happens first because of gravitational effects, but also because of cross-flow effects. And to visualize that, we have these two pictures here. So the first graph, we plot the ternary, water in blue, gas in red, oil in green. And on the bottom part of the picture, we plot the trapped gas saturation in the model. So first, if we take a look at the trapped saturation after the first gas lug, that being before we are injecting any water in the system, we see that we already have some gas trapped in the system. And that happens because of gravitational effects. So the gas tends to go up and the oil down. And so you have the inflow of oil in a cell being mostly gas, and you see some of the gas being trapped in our simulation. And the other effect has to do with crossflow. So we see that after we start injecting the water, most of the gas, you see a lot of gas trapped along the fingers. But that happens in part because of the water invading those fingers. But even where water has not reached, you see that there's a lot of gas being trapped in here. And that happens because when we inject water at the start of the fingers, you see crossflow of oil into the fingers. And this crossflow would then trap the gas or part of the gas in those fingers. And so in a way, a very large part of the gas is actually being trapped by the oil phase. And that raises an interesting question. In a near miscible scenario, yes, we're assuming that the oil traps the gas in our model, but maybe if you have interfacial tension between oil and gas with very small values, that trapping may not occur. So it's important to have further studies of the interfacial tension effects on phase trapping. And so to summarize our conclusions, first, we saw that WAG has the largest impact on the immiscible case. The WAG hysteresis model seems to work very satisfactorily for the near miscible scenario also. And hysteresis effects assist in the recovery of the heavier oil components in the near miscible case, at least in our simulations. For the miscible case, though, we saw that most of the CO2 is dissolving in the oil phase, and so there's very little gas phase in the system. And this affects the performance of the WAG hysteresis model. And that is because the model needs to actually see the gas phase in the system so that it can trap the gas or have the gas interfere with the water phase and so reduce the mobility of both the water and the gas phase. And if the CO2 is all on the oil, nothing of this will happen. And so we see almost no effects of the hysteresis model in the miscible scenario. And finally, we saw that a large part of the gas is actually being trapped by the oil phase. And so it would be interesting to investigate the effects of interfacial tension on phase trapping in the future.